All right, welcome to Unit 11. We're going to start off with 11.1, and our section is called Simplifying Radicals. So radicals are another term for our square roots. We've seen these before. We just haven't really simplified them. So go ahead and write down the objective. I'm going to kind of talk about a little bit what it is we're doing here. We're going to be able to simplify radical expressions. Remember, expressions, there's no equal sign. We simply just have an expression and we're going to break it down to its simplest term. We're going to have to use radical properties, and we're going to identify things like rational and irrational numbers, okay? And this is where we're connecting them to either their exact and or approximate solutions, depending on what it is we're asking for. Alright, so just remember, at any time you need to pause the video to write something down, or if you need to rewind the video, please go ahead and do that. Make sure you get all these examples down. That way you have an easy time working on the homework or classwork. Alright, so some of our things to know. If you look here, we have the parts of a radical. This is the anatomy of what our radical looks like. We have the radical symbol, the square root sign, okay? Like I said, we've all seen this before, but this is a good vocabulary for us to know. So if you have a value on the outside to the left of your radical, this is your big number that you usually see. Same thing like we see next to a variable. This is our coefficient. This is what is multiplying with the radical. Okay, so think of it just like we've seen coefficients next to our variables. The little sign above that's connected to the square root sign, or the radical sign, is called our index. This tells us which root we're going to do. Now by default, if you don't see a number there, it's always assumed to be a number 2. The first type of root that we're going to take is a square root, and this deals with the inverse end of our perfect squares. If you see a 3 there, it'd be a cube root, a 4, a fourth root, a 5, a fifth root, etc. Okay, and then here's a big piece of vocab also. We have our radicand. This is the value that we're going to take the root of. Okay, so you're going to see this here. And sometimes you'll see an exponent in here also. You might see something like that. Okay, but we'll deal with those in the examples. Alright, let's go ahead and dive right in. These are the properties that we're going to be using. Okay, so I went ahead and printed these out for you. You don't have to write these in, but we kind of need to understand them. And I'm just going to blow through them really quickly so you have an idea of what's going on here. If you have some number raised to a power and that power is identical to the index, okay, if you have an odd number, so something like here, we have -5 as the radicand raised to a 3, and we also have a 3 for the index. These 3's right here, being that they're the same value, are going to eliminate themselves, and we're able to keep this -5 value. Okay, that only works because we have an odd number, right? If you had something like -2 times -2 times -2, right? You have a series of negative signs. 2 of them will cancel out, and you're left with a negative number. Okay, that means we have an odd amount of negative signs. It's a little bit different when you have an even value, right? Because if you had -2 times -2, you have an even amount of negative signs, and those are going to cancel out and leave you with a positive. So if your index and your exponent underneath the radical sign are of the same value, right, like we see here in this example, then we have to have a plus or minus in the solution. And this is what we're going to see a lot in 11.2. Okay, these next ones are kind of our big hitters right here, right here, and right here. We might see some of these, so these are important as well, but we're definitely going to see a lot of these 3 that I put a check mark next to. The first one tells us if we have the nth root, remember when we say n, this could be any value, and we have a product inside, okay, some value A times some value B, we can use the product property and actually split these two apart. We can rewrite them to the same expression. We're just rewriting it. So if we look here, we have the square root of 24. We know that we can rewrite 24 as a product of 4 and 6. We did this when we prime factored and greatest common factor. We know that 6 times 4 equals 24. So I'm not changing anything in the expression by splitting this up. I'm simply doing this so I can actually get some exact values and simplify a radical. So I can have the square root of 4 times the square root of 6. So I'm able to pull apart this product here into this, okay? And if I want to, I can also go on the reverse end. If I had, let's say, the square root of 3 times the square root of 2, okay? If this product here breaks down to this, we can actually go the reverse and have this as the square root of 3 times 2, which is also 6. Okay, so you're going to be going back and forth with these a good chunk. This one here states the same thing as the product rule, but it's just the quotient rule. So on the opposite end of multiplication, we would be doing division right here. This one here, if we are adding or subtracting radicals, okay, similar to like we did with adding or subtracting exponents, we need to make sure that our radicand, okay, are the same, and also the index are the same. Our coefficients, okay, are going to be either the same or different based on what values we have. But if we have the same radicand, these values, and we have the same index, these values, then we can actually add the coefficients. So if you see here, we have a radicand of 8 and we have indexes of 2, so we can actually add the coefficients here. 7 plus 5 is 12, and we keep the same radical right here as the square root of 8. And the same also works with multiplying, okay? Remember, if you multiply here like we did with the product rule, but you actually have coefficients, make sure that you also multiply the coefficients. So 6 times 3 would give us that 18, and then you're multiplying the radicand, 5 times 4, and then you get that 20. This has to apply with the indexes being the same. Okay, so you have this in your notes. If you need to run this back and hear what I said again, please do so. But get very familiar with these properties here. Alright, so for example number 1, okay, it wants us to start simplifying by dividing by a perfect square. Okay, there's two different methods I'm going to show you here. And obviously I want you to use the one that works best for you. So if you remember your perfect squares, you know, those are 1 squared, 2 squared, 3 squared. I'm going to list them up here in this box. You can do so if you like. But we know we got 1, 4, 9, 16, 25, 36, 49, what's next, 64. Then we have 81, 100, 121, 144, 169. So this is all the way up to 13. These are a good chunk to kind of commit to memory. We might see some bigger values, and at that point just fiddle around with the calculator, see what you can come up with. Okay, so I'm trying to ask myself here, out of all of these perfect squares that I listed, which one of them can I divide by a perfect square without getting a decimal? I want to divide wholly into the radicand right here. So I obviously can't divide by a 9. A 9 is too large. So I want to kind of start going down the line and figure out which values I can divide by. So if I look to the left, something smaller, 8 divided by 4, pretty simple. We all agree that 4 does go into 8. So I want to actually split this apart, okay? using that product rule. I know that 4 times 2 will give me 8. So I'm going to rewrite this as the square root of 4 times the square root of 2. Okay? And you can write it like that, or if you want to, you can write it like this. I'm highly preferable to writing it like this because it's easier for me to see which of these values I can actually take the square root of and get a exact value as opposed to an approximate value. So if I take the square root of 4, I get a positive 2. The square root of 2, I cannot get an exact value. So this is going to be the most precise way for me to represent the square root of 2 unless I list out a series of decimals. So I can just multiply this 2 times my radical 2, and I have my solution here. Okay, let's try this next one. So 75, well, if I look, what's a number smaller than 75? 64, that obviously won't go in, neither will 49. 36 times 2 is 72, still kind of too big. 25 looks like a good one. So 75 divided by 25 gives me a 3. So I know that the square root of 75 I can break apart as the square root of 25 times the square root of 3. And we know that the square root of 25, right, that's our 5 times 5. So this becomes 5, and then I have my radical 3. All right, let's see, 108. What number can I divide into 108? 100, way too big. 49, maybe too big. 64, probably too big, right? Let's see. What about 36? Looks like 36 can go in. 36 times 3 will give me 108. So I can get the square root of 36 times the square root of 3. And square root of 36 is 6. So I'm left with 6 radical 3. Okay, so these 3 examples are all pretty much alike. Here on this next one, we're kind of introducing that coefficient. So the way that this works, we have this coefficient on the outside, okay? This coefficient is going to carry out. We can still split apart this because remember, this is a product. And if you remember our rules, A times B is the same as B times A. So we can move these around as we please because they're all multiplying to one another. So what number can go into 45? That's a perfect square. Looks like I'm going to have to use 9. So this is basically saying negative 4 times 9 times, what is that, 5? 9 times 5? Okay. What is the square root of 9? That gives us a 3. And then we have this radical 5. And then we just go down the line and simplify everything we can. Negative 4 times positive 3 is a negative 12. And then we multiply by the radical 5. All right, go ahead and pause the video. I want you to try the next 2 on your own. And then come back and see if you got the same solution. All right, welcome back. So you should have gotten, right? Remember, if we don't see a value here, it's always a 1. So this negative sign lets us know we have a negative 1 here. Let me go ahead and put that there for you. And we have a negative 1. Ooh, that doesn't quite look like a negative 1. How's that? Is that a little bit better? All right. Negative 1 times the square root of 4 times the square root of 5, and then we're left with a negative 2 times radical 5. Oh, I should have wrote it like this. Let's do it like that. That looks better. We don't need that little dot in there. All right, and our second one, we have the 5 on the outside. 18 splits up. It's divided by 9. 9 times radical 2. So we're left with 5 times 3 times radical 2. And 5 times 3 gives us 15. And we got the radical 2. All right, very good. I hope you guys got those and are kind of getting the hang of these simpler ones to simplify. Okay, so another way that we can do this is by finding our prime factors. And the reason why it's good to know this, because once we start simplifying the ones with variables, we're going to be pretty much using the same kind of technique for the ones with the variables. So let's go ahead and do a factor tree of 128. I'm going to do this off to the side here. Anytime you got an even number, remember we want to get down to primes. So it's best to start with a 2. Half of 128, I believe, is 64. Oops. And then 64 is the same as 2 and 32. 32 is 2 and 16. 16 is 2 and 8. 8 is 2 and 4. And 4 is 2 and 2. Alright, that's kind of long. But remember, we are using all of these side values here. So if we line this up in prime factored form, we basically have a 2 times, how many do we got here? 1, 2, 3, 4, 5, 6, 7. 2 times 2 times 2, that's 3, times 2, times 2, times 2, times 1, 2, 3, 4, 5, 6, and then times 2. So we got 7 of these 2's, okay? In this section, we're dealing with square roots only. So that means our index is a 2. Now what we want to do for this method by finding prime factors is we are looking for pairs of 2, and that's because our index is 2. If our index was 3, we would be looking for, can you guess? Groups of 3. So here we got groups of 2. That's because we have square roots. So as you can see, I have 3 groups of 2. And what we are going to do is we are going to take out from underneath the radical sign however many groups of 2 that we have. And when you do this, each group that you have is listed as a 2. Okay? So if I have one group of 2, that's a 2. I have my second group of 2, that's a 2. And my third group of 2, which is also a 2. Now I had 7 2's in there, so I'm left with a 2 underneath my radical. And then I want to go ahead and simplify this side. These are all being multiplied, so I got 2 times 2, which is 4, times 2, which is 8. So I'm left with 8 radical 2. Okay, I know this one might be a little bit confusing, but the more we do, the better we get. Alright, so let's try the second one here. We have 245. This is going to be a big one to factor tree. Alright, so I want to divide this by 5. Right, 5 is my lowest. So 245 divided by 5 is going to give me 49. Okay, then 49, well, we know that 7 is a prime number. 49 is actually a perfect square. So this actually didn't take us that long. Pretty nice. So here are our prime factors. We can write this as, right, I should have done that over here, but that's all right, as 5 times 5 times 7 times 7. So I got to ask myself, do I have any groups of 5? Nope, there's only one of them. I'm looking for pairs. I got a group of 2 7's over here. So I'm going to take out that group of 7's. Okay, and if I only have one group, that means I have only one 7 on the outside. So I have my group of 7's, as that 1, 7, and I have the remaining 5 right here. Okay, and if you wanted to do this with the method we showed in example 1, right, we can ask ourselves, well, 245 divided by what perfect square gives me a whole number, not a fraction, or not a decimal rather. We would have found that 49 times 5 is what gives us 245. Alright, I'm going to skip down to this one right here, and then I'm going to let you try the next 3 on your own. So you can get some practice in here. We got 18. If we factor tree this, we got a 2 times 9, and then 9 is 3 times 3. So remember, we're writing this underneath the radical sign as prime factored. I'm going to ask myself how many groups of 2 do I have? I don't have a group. There's only one of them, but I do have this group of 3's. Remember, this 5 is on the outside multiplying into the radical because it's the coefficient. So I now have 5 times. I'm taking out one group of 3. I got my 3 here. I got my radical, and there's a 2 right here. So then I get 15 radical 2. Alright, go ahead and pause the video here. Try these next 3 on your own. Unpause and see if we get the same thing. Alright, welcome back. So if you look here, 72 we broke down as 2 times 2 times 2 times 3 times 3. So in this case we had 2 different types of groups. We had a group of 2 and a group of 3's. That comes out as a 2 and a 3. And you're left with that 2 on the inside. So we got 2 times 3 is 6, 6 radical 2. Here we got 27. That breaks down into 3 times 3 times 3. So we got one group of 3. That comes out as a 3 times that negative 5, giving us negative 15 times what we have left under the radical. And our last one, we got 80. 2 times 2 times 2 times 2 times 5. We got 2 groups of 2 that we take out, which 2 times 2 is 4. 4 times that negative 4 on the outside, we then get negative 16 times the radical 5. All right, very good. I hope you guys got those, and they're getting a little bit easier for you. So these are the 2 different ways to go ahead and do that. All right, example number 3, we have multiply and simplify radicals. Okay, so we got to kind of work moving forward one way, and then doing some simplifying again after that. So what I recommend is always kind of look at your coefficients first. We know that those are going to multiply regardless, and then we also want to multiply our radicands. So if we get 4 times 2, that's going to give us an 8. And then when we multiply the 5 times the 15, we're going to get, what, 5 times 10, 50, times 5, 25. We're going to get 75. Okay, so now we've multiplied these 2 radicals, but we're not fully simplified yet because we can actually simplify the radical 75 using what we've learned from the previous example. So I like to just divide by perfect squares. Saves me a lot of writing time. And I know that 75 can be divided by 25. That was actually one of our examples. And that's going to be 25 times 3. So I can break this apart like so. And I'm left with 8 times, what is this? Times 5 times radical 3. 8 times 5 gives me a 40. And then I have that times the radical 3 right there. And my solution is finished. All right, let's try the next one. We have a negative 3 times a negative 5. That is going to give me a positive 15. I also have a radical 15 times a 10, so 15. Just so you guys can see the work going on right here. This is 15 times 10 under 1 radical. and then we do the actual math. 15 times 10, that's what, 150. And now I want to ask myself, which perfect square, largest perfect square preferably, can I divide this 150 by? Well, we got 100, no, 81, 49, no, looks like 25 is also going to be the biggest that we got. So I'm going to break this down as 15 times the radical of 25, and we know that 25 goes into 150 a total of 6 times. So we're then left with 15 times the square root of 25, which is 5, times this radical 6. And again, 15 times 5, that gives me 75. Next to this radical 6. Alright, so go ahead, pause the video here again, try the next two on your own, and come back for the solutions. Okay, welcome back. So this one right here, we got -5 radical 10 times 3 radical 12. We get the -15 times 10 times 12 is 120. The biggest number that can go into 120, surprisingly enough, was just that 4. So you got to play around with these perfect squares. Square root of 4 breaks down to 2, right? 4 times 30 is what gets that 120. Then that -15 times 2 gives us the -30 times a radical 30. Okay, and our last one, 4 times 4 gives us that 16. 6 and 12 multiply give us that 72. 72 can be divided by 36. It multiplies by 2, so we split it up like this. Square root of 36 is 6. 6 times 6, 16 rather, times 6 gives us that 96. And we're left times the radical 2. Alright, we got this example here, add or subtract 2 radicals. So remember, there is that rule. You need to have the same radicand and the same index, or the same root. So in this case, remember the value underneath the radical sign is our radicand. Looks like these two are matching. We have radicand of 12 on both terms, and we're both using the square root. So in this case, I can simply add my coefficients, which are these numbers here, and then I'm going to keep the radical the same. So a -3 plus a +2 gives me a -1, and I'm left with the radical 12. Okay? Fairly simple. It works really great if you have the same radicand. Looking at our next example over here, we're kind of in a little bit of a pickle. All right? Here we got a 2 times a radical 2, so we have a radicand of 2. And this one we have a radicand of 8. So we need to figure out, we want to ask ourselves, how can we write 2 radical 8 to match 2 radical 2, right? 2 radical 2, this radicand of 2, we can't just make bigger, but we can make 8 smaller, okay? So this is just going to involve a series of steps, right? We know that we're going to keep this the same because we can't just make values bigger when we square root, but we can make them smaller. How can we do this? Well, we need to look what perfect square can divide into radical 8. So we know that 4 can go in, so we want to rewrite this one as 2 times radical 4 times radical 2. Okay? And then remember, you should always tell a story when you show your work. We haven't done anything with this first 2 rad 2 yet, but we can square root the 4, which is going to give us a 2. So we got plus 2 times 2 times radical 2. Okay, everyone with me so far? So we drop down the 2 radical 2 again, And now let's go ahead and combine this side. We got 2 times 2, which is 4. And then we have the radical 2. Now you can see we have the same radicand. We have the same index. We can go ahead and add our exponents, giving us a 6 times the radical 2. Alright, not too bad. Alright, I'm going to do one more, and then I'm going to let you guys try the next one. Alright, so we got 2 radical 6 and 3 radical 54. And if you haven't already guessed from the first example, right, we're most likely trying to get the 54 to go down to a 6. So a good rule of thumb, a good practice I should say, try dividing your 54 by 6, right? We know we want one of these to turn into a 6 because the other is a 6. So more than likely it's going to end up dividing that way, right? So let's drop down our 2 radical 6. If you did the division in your head already, you can tell that 54 splits up into 9 times 6. So we got 3 times, radical 9 times radical 6. So let's go ahead and finish the work here. We know that radical 9 square root turns into a 3. And we have the radical 6 here. And we're left with 2 rad 6 plus 3 times 3, which is 9. Radical 6. Go ahead and add up your coefficients. And you get 11 radical 6. Very good. Alright, go ahead and pause the video, try the next one, come back and see the solution. Okay, welcome back. Alright, so what I got here, I dropped down my -3 radical 3. Remember, this was my smallest part. I went ahead and broke down this radical 12. Okay, so I know that 4 times 3 gives me a 12. I was able to square root the 4, which gave me this 2 right here. And then I got the times radical 3. And -3 times 2 gives me a -6 times my radical 3 is what gives us -6 rad 3. And I just simply subtracted the coefficients. And remember, -3 minus a 6 is going to give us that -9. Alright, very good. We're almost done, guys. Hang in there with me. Okay. So our last example, we have, oh man, we got numbers and letters, okay? Integers and variables for the layman. All right, what we want to do, we're going to treat this value here, our radicand of the number variety, as the same as we've been doing before. Okay, the only thing that's different here is we have these variables. And this is where we might want to do that prime factoring and think about the whole idea of groups. So what I might want to even do, okay, and remember, the more that you do these, your method of how you break these apart and write them can vary, but if you know your algebra properties, you should be able to do them in a variety of ways that are still correct. Since I know that these are all a product, right? These are all factors that make up a product. 144 times m squared times n squared. I can break these up into 3 different parts. Okay? So now I want to think, well, do I need to break down 144 or is that a perfect square already? Well, 144 actually can be divided by a perfect square, 144, and that is a 12. So let's just go ahead and square root that. We got a 12. Okay. Then if I look at my variables, okay, if I prime factor them, remember, if we think about our exponent rules, remember the way that we add exponents is we multiply the same base. So we can break this down. We know m squared is the same as m times m. And let's go ahead and do the n's over here. We got n times n also. Sorry, these connect for some reason. Get my little time sign. All right, so remember, we're looking for groups of 2. Well, I got 2 m's, m and m. And I got n and n. All right, so that's also a group of 2. You see what I did there? Well, if I have a group, a pair, I take them out the same way I took out a pair of number values. So one pair of m's gets taken out as a single m. And I do the same with my two n's here. So I have one group of n's, a group of two, so that comes out as 1n. Okay, and then I got 12 times m times n. Let's go ahead and clean this up. We don't need those little time signs. We can write our solution as such. Okay, so not too bad. But what you can notice here, if I have an index of 2 and I am taking out groups of 2, then if my variables here are only squared, then they're basically going to come out of the radical sign and will no longer be a radicand. Alright, so let's try this one right here. We got 24. Let's separate this out. Square root of 24 times, let's separate these. You know what? I'm going to leave both of these in here because I want to show you another trick before you get to the bottom here. And v to the fourth. Alright, so 24 looks like I can divide it by a 4, probably being the biggest number. So this is going to be radical 4 times radical 6. And if I'm looking for groups, right, how many groups do I have to match this, right? If we looked at our previous, remember our properties list, we know that if they're the same, we're left with what's standing alone right here. Okay, so here I have 4 v's, right? I can divide this by this. How many times does 2 go into 4? 2, so that means I'm going to have 2 groups of v's. Okay, and it's going to go in evenly, so I have nothing remaining. All right, now let's go ahead and simplify this. We got square root of 4 is a 2. We have a radical 6, and we have a u and a v squared. And when we clean this up, we like to keep the radical at the end. So I might write my solution as 2u v squared radical 6. And remember, these are all factors, so if you have it in a little bit of a jumbled up order, I'm not going to mind too much, but you should get in the habit of cleaning it up to look something like this. Alright, see if you can get the next two on your own, and then come back and we'll talk about it. Alright, welcome back. So I kind of guessed you might have had a little bit of trouble with these two because, boom, we had these odd exponents in there. Okay, so basically we're doing the same thing, but when we're looking for groups, we can't have a group of 2, right? If I got 7 students, I can't put everybody into pairs. Okay, so we do the process the same, right? 54 I'm able to split up as 9 and 6, which the square root of 9 is 3, and then I get the radical 6. Now here, when I'm looking for my groups of 2, right? If I have a to the third, that means I only have one group of 2. So that's why I only took out 1a. B to the fourth, I have 2 groups of b, right? So I'm taking out a b times a b, which gives me the b squared. But I had the remainder a, okay? So when you have an odd number, you're always going to have a single one left inside as the radicand. Now if we look here at this portion, okay, we can go ahead and multiply the coefficients, which is 3 times ab squared, which I got right here. But I also need to multiply the remainders of my radicands, and I use that same product rule. So 6 times a is going to give me a 6a, leaving my final solution here. Okay, and the same goes for this side. We have a radical 64. That's actually a perfect square, so we can square root it down to an 8. I only had one group of 2 with a remainder of 1, so I took out my one group of two x's, and I had a remainder of 1x. I took out my one group of y, which left me the y on the outside as the coefficient, and then I clean it up by combining all of my factors, giving me 8 times x times y times my radical of x. Okay, so that's it for all of our examples. I gave you guys a good healthy chunk of practice problems to work on. Please use each other as resources. Get this work done in class. That way you guys are prepared for the quiz and also for the upcoming unit exam. Thank you for your time. I'll see you guys in the next lesson. Peace.